everyone, thanks so much for joining for this video. Here are today's learning objectives. They're all to do with bonding and physical properties. So we're going to look at the 4 types of crystal structure: ionic, metallic, macromolecular and molecular. And then we're going to look at a few examples of the types of different structures. And we're also going to look at how to relate the melting point and conductivity of materials to the type of structure and bonding. Also to explain the energy changes associated with changes of state, and also to be able to draw diagrams to represent these structures involving specified numbers of particles depending on the question. So our first example is diamond, and diamond is made up fully of carbon atoms, and they all form 4 single bonds each. So there'll be single covalent bonds, and because carbon is non-metal, that's how we know that it's covalent. We call this an allotrope of carbon, which just means that an allotrope is basically something that can have lots of different forms, but is made by one element. And it's a 3D lattice, so it's macromolecular, which is giant covalent. We're going to learn about bond angles a bit later, but the bond angle is 109.5 degrees between the atoms. So it kind of forms a tetrahedron in the corners. So some of the physical properties are that it's very hard, it's got high melting and boiling points, and it does not conduct electricity. So it's very hard because the covalent bonds are really strong, so it's hard to overcome. The covalent bonds are also the reason why it's got high melting and boiling point, because they're so strong that it takes a lot of energy to break them. And it does not conduct electricity because it doesn't have ions and it doesn't have any delocalized electrons either. So nothing can carry a charge. The second example is graphite. And this is another allotrope of carbon. So it's also made up of just carbon atoms. There's very strong covalent bonds between the carbon atoms. So in the hexagons that we can see, here, for example, all of these blue lines are strong covalent bonds, but there's weak forces between the layers, and we're going to learn later that they're called van der Waals forces, and these are the red dots. So each carbon atom actually forms 3 single bonds each to another carbon. So that means that every carbon has 1 spare electron in their p orbital to form a 2D sheet. So here we have 3 2D sheets. And so the p orbitals above and below each sheet merge, and the electrons become delocalized, so they can move within the sheets. So that gives it very special properties, which we'll have a look at in a second. But the bond angle is 120 degrees, and we call that trigonal planar. So some of the physical properties is that it can conduct electricity, it's a soft metal, and it has high melting and boiling points. And it can conduct electricity because of the spare electrons in the p orbitals, because they're delocalized, so they can carry the charge. It's a soft metal because the layers can slide over each other. So graphite is used to be found in pencils. So when you write on a piece of paper, it writes really well, and that's because the layers of the 2D graphite sheets can slide over each other really well because there's only weak forces between the layers, and so it's not hard to overcome them. So that's why it's a soft metal. It's got very high melting and boiling points because of the very strong covalent bonds, because we're not trying to break the weak forces, we're trying to break the really strong covalent bonds, and that's why it's got a very high melting and boiling point. But for when we're trying to break the layers, we're just breaking the weak forces between the layers, so that's why it's soft, but then it also has a high melting and boiling point. For ice, this diagram is only a small part of the structure, but it has quite a low melting and boiling point. And that's just because it's quite small, but we'll go on to the structure of ice a bit later. Example number 4 is iodine, and it's a simple molecular crystal, so it's covalently bonded, but it's not a macromolecular structure, so it's not a giant covalent. There are strong covalent bonds between the iodine atoms, but there's weak van der Waals forces between the molecules. The iodine molecules have lots of electrons, so the van der Waals forces are strong enough to hold it as a solid, so as like a crystal. Some of the features, some of the physical properties are that it has a low melting boiling point. That's because the forces between the molecules are very, very weak, so we can break them easily, so it doesn't take very much energy to overcome. They're soft and break easily. That's kind of the same thing, so it doesn't take very much energy to overcome. And it cannot conduct electricity, and that's because it doesn't have any ions or delocalized electrons to carry the charge. Next, we move on to magnesium, and this is an example of metallic bonding. And so there's very strong electrostatic forces between the positive ions and a sea of delocalized electrons, which are negative. And so we get a high melting and boiling point. They're very strong and hard. They can also conduct electricity and heat because of the free electrons and because the ions are so packed together that they can vibrate about a fixed spot and then vibrate the next one, and heat can be conducted that way. And we've also learned that they can be malleable and ductile as well. Sodium chloride has a giant ionic structure, and that's because it's made out of a metal and a non-metal. So there's strong electrostatic attraction between the oppositely charged ions. This means that it can conduct electricity when molten or aqueous, but not when it's solid because the ions are fixed in place. They are strong, also because of the strong electrostatic attraction, and they have high melting points and boiling points because the electrostatic attraction between the oppositely charged ions takes so much energy to overcome that a lot of heat is required. So now we're going to look a bit on solubility. Simple molecules are usually insoluble in water as they're non-polar, and water is actually polar. And because simple molecules are non-polar because they're covalent, so they're non-metals, they can't really bond together, so they tend to be insoluble in water. But they usually dissolve well in organic solvents because organic solvents are also non-polar, so intermolecular forces are formed between the solvent and the solute molecules. Ionic compounds are usually soluble in water, and that's because water is polar. Ionic compounds are also polar. And then ionic compounds are also insoluble in organic solvents because they're polar and organic solvents are non-polar. Compounds with hydrogen bonding are soluble in water, and that's because they basically have the same bonds, because we'll learn later about hydrogen bonding, but hydrogen bonding occurs between a hydrogen and a very, very electronegative atom. And also compounds with hydrogen bonding are insoluble in organic solvents. Metallic compounds tend to be insoluble just because it's quite hard to break the bonding to form bonds with the water or the organic solvents, and that's the same with the giant covalent structures. So now we're going to look at some energy changes. The term enthalpy just means the heat energy change, which is measured under constant pressure. And so going from a solid to liquid, what happens is that the solid gets heated, and initially it causes the atoms to vibrate about their fixed positions, and the solid expands because of this, and the temperature rises. But during melting or fusion, energy is absorbed to weaken the forces between the particles, so the temperature actually becomes constant because all the energy is being absorbed to weaken the forces instead of causing the atoms to vibrate more. And so that energy is actually called the enthalpy change of melting. So the heat energy change required to melt it. And when it turns into a liquid, if you continue to heat it, the atoms move with higher velocity, so they have more kinetic energy. And so the liquid expands and the temperature rises. But during vaporization, which is when the liquid turns into gas, the energy is absorbed to break all the forces between the particles. Because in a gas, there's no forces between the particles. They're all just moving separately by themselves. And so the temperature is constant because, again, the energy isn't being used to move the atoms more. And this energy is called the enthalpy change of vaporization. When it turns into a gas, if you continue to heat it, it just causes the atoms to move about with even higher velocity, and so the gas expands and temperature rises. So if we kind of look at a graph of changing states, so if this is the temperature, then first of all, when you say we start off with a solid, the temperature rises, and then at some point it will turn into a liquid when it reaches its melting point. So say this is its melting point. And when it reaches its melting point, the energy is absorbed to weaken the forces. So then the temperature becomes constant, like this. And so now it's become a liquid. And then the temperature rises again. And this isn't necessarily the same gradient as this one, but this is just a generalized way of looking at a graph of melting and vaporizing. And then when it reaches here, it's reached its boiling point. And the temperature becomes constant again. And then, so now it's a gas. And then the temperature continues to rise once you heat it up again. So here, this is all solid. And here, it's a liquid. And here, it's a gas. So now we're going to move on to some questions. The first one is to explain why graphite can be used as a lubricant. And this is because even though all of the carbon atoms are covalently bonded together, so they have very, very strong covalent bonds between the carbon atoms, there are weak intermolecular forces between the layers of the hexagonal 2D sheets of carbon, kind of hexagonal rings. And this is because one of the electrons from the carbon has been donated to an electron cloud. So the p orbitals overlap and the electrons become delocalized, and that's why we get the weak forces between the layers. So that means that the layers can easily slide over each other, so it can be used as a lubricant. For number 2, describe what the difference is between a macromolecular crystal and a molecular crystal in terms of the following: bonding and properties. So with bonding, macromolecular means giant covalent, and molecular means simple molecular, so just molecules. The bonding in a giant covalent is very, very strong bonds between the atoms. So and in molecules, the bonding is strong covalent between each atom, but between molecules, there's very weak intermolecular forces. And so for the properties, that means that a macromolecular crystal has a very high melting point compared to a molecular crystal, which would have a very, very low melting point because of the weak forces that we're trying to overcome, because we're not trying to overcome the very, very strong covalent bonds between the atoms. We're actually breaking the weak intermolecular forces between the molecules. Whereas in the macromolecular crystal, we're trying to break the strong covalent bonds, which obviously takes a lot of energy to overcome. So it has a very high melting and boiling point. Hi everyone, thanks so much for joining this video. We're going to look at some harder questions for the bonding and physical properties of different compounds. So the first question is to explain how graphite conducts electricity and how it conducts differently from other metals. So graphite is made up of carbon atoms, and they form hexagonal 2D planes. And one of the electrons from the carbon is donated to a p orbital, like an electron cloud, and p orbitals overlap. The p orbitals above and below one of the 2D planes overlap, and so the electrons become delocalized and they can move in between the layers of the graphite. So because the electrons are delocalized, that means that we can conduct electricity using graphite. However, in metals, metals are structured with positive ions all together, and they exist in a sea of delocalized electrons. So again, it has delocalized electrons, so they can carry a charge and conduct electricity, but it is slightly different to graphite, even though graphite has kind of metallic properties if you think about it, but they are slightly different. So for number 2, perfume is a mixture of fragrant compounds dissolved in a volatile solvent. When applied to the skin, the solvent evaporates, causing the skin to cool for a short time. After a while, the fragrance may be detected some distance away. Explain these observations. Okay, so this is a bit more of an applied question, but basically what happens is that when you apply it to the skin and the solvent evaporates, and when something evaporates, it actually takes away heat, because energy is required to turn it into a gas. So that's why the skin cools for a short time. And then after a while, the fragrance is detected because of diffusion. So in the air, it's carried some of the particles of the perfume in the air, and that's why you can smell it some distance away.